an electron configuration is simply a listing of the number of electrons assigned to each subshell. Okay? So, for example, when you write something like 1s2, 2s2, 2p1, what does that mean? We're assigning 2 electrons to the 1s orbital, right? 1s subshell. We're assigning 2 electrons to the 2s subshell, and we're assigning 1 electron to the 2p subshell. Now, when you write electron configurations, if you don't write a number, the superscript, it's implied to be 1. Okay? So if I write something like this, 1s2, 2s2, 2p with no subscript, that number there is implied to be 1. It's not implied to be 0. In chemistry, most of the time, when we omit something, we mean 1. And like, for example, when you write a formula CH4, what's the implied subscript for carbon? 1. So in this particular case, you also, if you omit the number in your electron configuration, that's implied to be 1. So here's some quick review questions from freshman chemistry. Which of the following can have an electron configuration of 1s2, 2s2, 2p1? We're dealing with something here that has how many electrons? 2 plus 2 plus 1 has 5 electrons. So it's really a question of which of these has 5 electrons, right? So lithium with 2 negative charge, what would that be? How many electrons per lithium atom? 3 electrons, and the negative 2 more electrons is 5 electrons. So lithium is okay. Whether it would actually exist in nature or not, if you had such a thing, it would have 5 electrons. This would be an electron configuration for that. Right? How about boron? Atomic number of boron is 5, so boron has 5 electrons also. How about carbon with a +1 charge? Carbon, atomic number 6, so carbon would have 6 electrons, but the +1 charge means 1 electron lost. So carbon with a +1 charge has 5 electrons. So all of these can have an electron configuration of 1s2, 2s2, 2p1. Okay? So the answer is all of the above. Anything that has 5 electrons. Any atom or monatomic ion. Which of the following is not a valid electron configuration for a lithium atom, which has 3 electrons? Which one? A. Why? Because an s orbital, an s subshell is just 1 orbital, the 1s orbital, and in an any orbital you can only put how many electrons? 2 electrons. So this is not valid. Okay, so this is the correct answer. 1s2, 2s1 is okay. There's nothing wrong with 1s2, 2p1. That just happens to be not the lowest energy state, not the ground state. That would be what you would call an excited state, okay, of your molecule, of your atom. 1s1, 2p1, 3s1. That's 3 electrons right there. So all of these are electron configurations for an atom or an ion that has 3 electrons. So there's nothing wrong with any of those. Okay, as long as you do not violate Pauli's exclusion principle. Ground state configuration is the most stable, the lowest energy configuration, and like I said earlier, you can also have excited states. Some configurations would correspond to a higher energy state. So which of the following is the ground state for hydrogen? What do we know about the energies of the electron in a hydrogen atom? E sub n. For hydrogenic atoms, E sub n is negative 13.6 electron volts over n squared, right? So what's n here? N equals 1. What's n for this one? N equals 2. What's n for this one? But we're looking at the ground state of hydrogen, so it can't be this one, right? Well, what's wrong with B? You've got 2 electrons. Hydrogen has only 1 electron. So the answer is lowest possible energy configuration for electron configuration for hydrogen atom would be if your electron is in the 1s orbital. Okay. If it's in the 2p orbital, that would be an excited state, and we've talked about that before. Electron in the 2p orbital could eventually lose a photon, lose energy by releasing a photon, and that gives you your what you call your Lyman alpha line, right? From 2 to 1, n equals 2 to n equals 1. What's an excited configuration for helium? You can write 1s2 would be the ground state, right? Because you can put as much as 2 electrons in the 1s orbital. So what's an example of an excited state? Like 1s2s, 1s1, 2s1, or you can have 1s2p or 1s3p. So anytime you don't, if you don't put everything in the 1s orbital, the lowest possible energy orbitals, then you have an excited state. The alpha principle is also known as the build-up principle. Gives you an electron configuration with the lowest possible energy by assigning electrons to the orbitals that would have the lowest possible energy. Okay, and so if you want the ground configuration, the lowest energy electron configuration, all you have to do is assign your electrons to the lowest possible energy orbitals. And keep in mind when you do this, you have to follow Pauli's principle, Pauli's exclusion principle, no more than 2 electrons per orbital. Now, typically, you can get the lowest energy electron configuration or the ground electron configuration by filling in, assigning electrons, okay, to orbitals that have a lower n plus L value. So the typical order in which the orbitals are filled, you go by the n plus L, the sum of the n plus L quantum number. If 2 orbitals have the same n plus L, then the one that has a lower n, if you fill that one first, you typically would get a lower energy, overall energy for your configuration. Okay? So here's an example. In a typical atom, which of these orbitals would an electron have a higher energy? 3s, 3d, or 4s? If you were to fill these orbitals, which one would you typically fill first? Well, let's use the n plus L rule. For 3p, n is 3 and L is, L, remember, is a code for S, P, D, and F, right? So 3pL equals 1, so 3p n plus L is 4, right? What about 3d? N is 3, L is 2. So you'd have a higher energy for the 3d. How about 4s? N equals 4, L equals 0, so that's 4. So which one, in which of these orbitals would the electron have a higher energy? In the 3d. So you would get, so how, in what order would you fill this? If you were to try to go for the ground configuration of an atom, what order would you typically fill these orbitals? Okay. All right, so we know 3D has the highest energy, right? You have a tie here between 3P and 4S. Which one would have a higher energy? The one with the larger N has a higher energy. So 4S, and then 3P. Okay, so if you remember the order that you construct your electron configurations, you do 3P and then 4S and then 3D. Okay? So typical atom, which of these is filled last? Ground state. Okay, let's look at our N plus L. This is 3 plus 1, 3 plus 2, 4 plus 0, 4 plus 1. So that's 4, 5, 4, 5. So we have to break the tie between 3p and 4s. Which one goes first? 3p first, and then 4s. Tonic that you can use, a memory aid that you can use based on the periodic table. Okay. The sequence that the orbitals are filled would be 1s first, and then 2s, and then 2p, 3s, and then 3p, and then 4s. After the 4s, it's 3d, and then 4p, and then 5s, and then 4d, and then 5p, and so on. If you remember, look at your periodic table. What do you notice about this so-called p block? We call this your p block in your periodic table. There's 6 columns there. Right? You can relate that to the fact that your p subshell can accommodate how many electrons? Up to 6. 3 orbitals times 2 electrons per orbital gives you 6 maximum capacity for each p subshell. Your 3D block, your D block right here, how many columns do you have there? Look at your periodic table. That's column 3 through 12. That's 10 columns. A D subshell can accommodate as much as 10 electrons. And then right here, your first 2 columns, that's called your S block. Okay, there's 2 columns there. How many electrons can you assign to an S subshell or an S orbital? 2 electrons. So this is a good way to remember the sequence. And one thing you'll notice here, there's a break in your periodic table. After 6s, okay, you do 4f first, and then you go 5d. And then between 7s and 6d, that you fill the 5f first. Okay, so you'll notice there's a break. If you look at the atomic numbers in your periodic table, there's a break there when you get to the 6th period and the 7th period. Okay. So let's write the electron configuration for scandium. Scandium's right here, number 21. So how many electrons do we have? 21 electrons. So 1s, 2, 2s, 2, 2p, 6, 3s, 2, and then 3p, 6, and then 4s, 1, and then after the 4s, what comes next? I'm sorry, 4s2, and then after the 4s comes 3d1. Okay, do we have 21? 2 plus 2 plus 6, that's 10. 2 plus 6 plus 2, that's another 10. That's 20. And that's the 21st electron right there. So that's the electron configuration. Okay? So that's, if you were to find the pattern here, the electron configuration is going to end with D1 here, D2, D3, D4, all the way to D10, although you may see exceptions here and there. And that has to do with the fact that these patterns that we're seeing here is just general patterns, but ultimately determines how these are filled. You can do the calculations for those. Okay? So there's subtle details that are generally not covered in your freshman chemistry textbook, and those are people tend to justify those, all right, and they're not really that easy to justify, because there's just as many exceptions to the justification. So, but you know, there have been, if you look at some textbooks, there have been attempts to explain those exceptions. When you get half-filled subshells and things like that, but even those explanations are, you know, what's the word? Tenuous. They're not, you know. You might see an exception that works for one period will not work for the next period. Ultimately, it boils down to that's just the way nature is, and that's just it. So there's a lot of subtleties that are not really addressed in the orbital approximation. First thing to realize is this: what we're doing here is it's an orbital approximation. Okay, we have not fully accounted for everything by just writing an electron configuration.